like to go over some exam problem and make an association with the potential topic for the internal assessment and extend the essay with possibly something called the Bernoulli numbers and Maclaurin series of a tangent. Okay, but moreover, I like to take this opportunity to emphasize the importance of working with textbook. Right, for the past few years, especially since the COVID era, since the COVID season, people tend to work with the online materials, right? And I have no problem. I think it's very helpful resource to work with the online materials to learn math. However, I don't think it's got that characteristics. You see, I don't think it's characteristics of a teaching style. But on the other hand, if you go over many publications, such as the most top-notch, Hayes, Pearson, Hodder, Oxford, IBID, if you will, contain their significant character of working. Especially, it's got many great examples to demonstrate certain topics. And online resource, however, often tend to be very concise and lacking explanation as what's going on. It's just more of teaching you to tackle problems, right? So, and that, of course, could polish you to prepare well for the exam, but maybe lacking the potential topics for the IA or EE. So today I'd like to go over the importance of textbook by demonstrating some exam questions, for example, from 2023, and a great similarity, as you can see, from an exam question on the Cambridge Press. Okay, but as you can see, what I'm trying to say here is, yes, it's very important that you're exposed with such problem before with the study of a textbook that you could have then attempted well on the actual exam. Okay, so so without further ado, let's get started. I want you to please, after this video, realize two things. Okay. Yes, it is important to gain some insight from challenging exercise on the textbook that I would not just skip over. And secondly, today I'd like to talk about a specific example of a tangent and its general formula of the Maclaurin series and why we don't learn it in the class. And if you remember, the trigonometric function that we learn with the Maclaurin series is to do with the sine or cosine. We don't really work with the tangent, and today let's try to derive it using the technique from the exam. Okay, so another exam problem that we could have seen, my friend, is take a look at this page 664 of the Hayes question number 2. It says it talks about the Maclaurin series of the exponential, and then it suddenly talks about something called the hyperbolic sine and hyperbolic cosine, which is not in the syllabus. However, it's definitely examinable. It did appear on the paper 3, and if you look at the question number 3, it uses the Maclaurin series of a sine, cosine, and exponential to derive the Euler's formula for the complex number. And if I show you the example on the actual exam on the May 2000, I think it's November, I'm not quite sure, but nevertheless, indeed, the paper 3 problem deals with this hyperbolic cosine and hyperbolic sine. Yet it does not tell you that it's a hyperbolic sine and cosine, right? But even though those learning phase and proving phase on the paper 3 seems quite new, you could have actually been exposed by textbooks, right? So that's the point I'm trying to make, right? So those are challenge problems, especially with the paper 3. It's good to gain the insight from the text problem. So yes, in the November 2021, paper 3 problem was something to do with the hyperbolic sine and cosine. I'd like to discuss a bit more on that, especially with the complex number and how we can derive the hyperbolic sine or trig sine, trig ratio sine, and then discuss their Maclaurin series and then make further extension with the cotangent, right? Okay, so what does that mean? Let's talk about it, right? So complex number and hyperbolic trigonometry. Let's get started. So yes, this is the typical Euler's formula, right? And if you actually see the sum and the conjugate, the sum of complex and conjugate, we know only the real parts left, which I know it is going to be something of a cosine. And then if you look at the difference of a complex and conjugate, we know it's going to be something of a sine, the imaginary part. But if you divide by 2, I get the I times the imaginary part of the sine. This is the typical identity for the complex number, no problem. Right? And then if you put now the theta as a complex number Ix, okay? For example, on the sine, right? So let's try to put the Ix on the sine. If I did, I squared is -1, so this becomes e to the power negative x, and this becomes double negative, so e to the power positive x, okay? And I'm going to divide by the I, but if you rationalize by multiplying the I and I on the top and bottom, you realize this becomes -1 then you can put it into the numerator, so that the conjugate minus complex will be swapped as a complex number minus conjugate. So therefore you can convert the following like this is what I have. Okay, so this is one way to represent the complex number on the side, right? And then so how does that help me? Well, let's have a look how it helps me. So we define the hyperbolic sine and hyperbolic cosine as the following. Hyperbolic sine function from the exam question was the difference of the exponential growth and then the decay over 2, right? So this was a definition of a hyperbolic sine. That's great. So let me try to multiply this by I, okay? So on this one, I realize that this is the complex number minus conjugate over 2, which would have given you the, I sine x, right? But if you multiply by the I again, this will give you negative sine x, okay? And that is the same as a sine of ix, as we have seen before, right? So you can actually associate with the hyperbolic sine and hyperbolic cosine, etc., etc. If I also remind you about the hyperbolic cosine, it was the average of the exponential growth and decay. And then remember, cosine theta was the sum of the complex number and its conjugate. But if you had replaced theta with the ix, you realize that this would be then e to the power of x plus e to the power of negative x over 2, for which you can see that it's a hyperbolic cosine definition, hence we can call it cosh x, right? So yeah, that's great. So if I give you the summary version of these trigonometric relation as well as the hyperbolic trig, is merely just to substitute the complex number inside of a trig that will result in the hyperbolic cosine, right? So that's the relation we can derive. So that was the exam question in November 2021. All right, so that is great. Let's have a look how we can associate with that on the Maclaurin series. All right, so deriving the hyperbolic sine or cosine Maclaurin series is rather trivial because it's made out of the exponential function, and exponential function of the Maclaurin series is very straightforward. And as you can see, if you have a sum of exponential as a Maclaurin series, for which we know the formula, it's going to be 1 plus x squared over 2 factorial. And I got the e to the power of negative x, which then will alternate depending on the odd terms. So it's going to be 1 minus x plus x squared over 2 factorial minus x cubic over 3 factorial. So notice for the odd term, it's going to alternate. What I mean by the odd term is this is the first term, this is the 0th term, isn't it? So therefore, as you can see, if you see the difference, the even term cancels out. Only the odd term gets double. But if you divide that by 2, then voila, I see the Maclaurin series of a hyperbolic sine, which then you can see it's quite similar to the Maclaurin series of a sine, but without the alternating term. And then likewise for the hyperbolic cosine, no problem. If you ask me why are we talking about the Maclaurin series of a sine, sine and the cosh, is because I want to associate with the Maclaurin series of a hyperbolic cotangent. Okay, so what do I mean by the hyperbolic cotangent? Let's have a look at this, the rational function as such, right? And as you can see, this is the growth and decay sum and difference. So if you divide the numerator and denominator by 2 arbitrarily, then you can associate the numerator by the hyperbolic cosine and then denominator by the hyperbolic sine. So I've got the following function, for which I know that it's going to be the hyperbolic cotangent. Yes, sir? So that's great. Well, that's how we define it, right? So the sine of a cosine is a tangent, but if it's a cosine of a sine, that's cotangent. But if it's a hyperbolic cosine over hyperbolic sine, we define as a hyperbolic cotangent. So that's what we have here. Okay, that's very good. And what I want to do is to derive the Maclaurin series. And how we can derive the Maclaurin series, knowing the hyperbolic sine and cosine Maclaurin series, is the following. It's in the syllabus. For example, when you were to derive the Maclaurin series of a tangent, right? You could have differentiated this many times and then plug it into the 0 to find the particular term. But it's rather quite complicated because if you differentiate this tangent, I get secant squared. And if you differentiate the secant square, I gotta use a chain rule. And after the chain rule, if you wanted to differentiate again, you gotta use a product rule. And it's just derivative gets very, very, very messy. But for the tangent function, if you want to derive the Maclaurin series of a tangent, what we can do is to work with the sine x and cosine x. And then tangent is even and odd. What is it? Very good. It is an odd function. So I'm going to just associate with the odd term, meaning I'm going to go with the a1x and I'm going to jump to the a3x cubic and then a5 x to the power 5 plus on and on. This is a typical exercise of the Maclaurin series problem in the IB syllabus. However, you are not expected to find the general formula because it's really quite complicated. But instead, if you wanted to go up to the fifth term, for example, then what you could have done is to use the Maclaurin series of a sine and cosine. For the Maclaurin series sine is some of that's a series of all terms, but they're alternating, so it would have been x minus x cubic over 3 factorial, x plus 5 over 5 factorial, on and on and on. For the cosine, it's an even function, so I'm going to do 1 minus x squared over 2 plus x plus 4 over 4 factorial, on and on and on. And then you, what do? You let this to be the same as the right-hand side. You let the right-hand side to be the same, and then you multiply this numerator to the right-hand side and compare the coefficient. That's what you did on the deriving the tangent. And I'm going to do exactly the same thing for the cotangent. If you think about, this is a even function, this is an odd function. The ratio of even and odd will result in the odd. So I'm going to be just dealing with the odd terms here. And I'm going to use the Maclaurin series of hyperbolic cosine and hyperbolic sine to derive the general formula of the hyperbolic cotangent and its Maclaurin series. Let's see how we can do that. Okay, so the preparation is that to realize that the hyperbolic cotangent is hyperbolic cosine over sine, and then and yes, I'm going to use the Maclaurin series of hyperbolic cosine. It's very similar to that of a cosine, but without the alternating term. But it was x over 2, so I'm going to sub it in the x over 2 to derive the following form. And if I do the same thing for the hyperbolic sine, which is similar to the Maclaurin series of a sine, but just without the alternating term, you get the following series. And I'm going to put that top and bottom respectively and then use it for deriving the hyperbolic cotangent Maclaurin series. So let's take a look. So I do that, and then this is going to be made of a bunch of the odd terms. It's going to be a1x, a3x cubic, a5x plus 5, on and on and on. Right? Let me quickly show you that. Right? So if I do that, I get the following odd terms. Okay? So that's brilliant. However, there's a little bit of a strange term that we do not usually see for the hyperbolic tangent. Sorry, the Maclaurin series. In fact, we got everything odd, such as 1, 3, 5, 7, 9. So that's brilliant, okay? But in this term, however, there's a strange behavior going on with the 2 over x, but by no chance, this is still the odd but the negative number, such as a negative 1, okay? So that's quite odd. So what we want to do is to get rid of it, right? So how I'm going to get rid of it is actually to multiply by the x over 2. So now I had the odd function, but x over 2 is surely odd function. The product of odd and odd would result in the even. So this is an even function. So as you can see, I got the to the power of 0, 2, 4, 6, 8, 10, etc., etc. That's brilliant, okay? So I got the even expression. And then when you look at this, right, how can I use it? Now, what are we talking about? We start with the November 2021 exam paper, and then we said that it's important to work with the textbook because they give you a lot of interesting ideas. And I got the idea that I'm dealing with the hyperbolic sine and cosine using the trigonometry and complex number. And using that, I got the expression of a hyperbolic cotangent as I asked you to do. But what is it? Well, the main aim that we established in the beginning of the video was that I wanted to derive the general formula of the Maclaurin series of a tangent. And this is going to be used for the tangent. But I need one more thing. Actually, I need two more things from the exam paper and then the textbook to build every pieces together to merge into something greater outcome as a tangent. Okay, so now I'm going to put a pause on this part right now. I'm very happy that I got this even expression of the hyperbolic cotangent with the product of x over 2, resulting in this following the Maclaurin series. But I'm going to derive something more significant and see the meaning of those coefficients. Okay, not yet, right? We cannot derive something of the Maclaurin series of a tangent yet with these numbers, but put a hold on it. Let's move on to the next video. Sorry, next chapter. So now next chapter, I'm going to get another insight from exam problem that has popped up very often these days on the paper 3, especially for the May and November 2022 in a row. It's something to do with the Power-Haber's formula, right? It's a power series, right? And so, from the old era of the IGCSE additional math, when you're working with the sequencer series, you get to learn about the triangular number, remember the first difference and second difference and third difference, things like that. It is to work with the power series. And let me quickly remind you what the power series looks like. So power sum, right, is, it's a sum of integer, it's an arithmetic series. We know it's just n times n plus 1 over 2 thanks to Gauss. And now let's have a look at the sum of a square. And this is the typical induction exercise, isn't it? This is left as an induction exercise to work with the induction hypothesis, implies the result, the proof. And this is quite a famous result. But the sum of cubes could also result in the perfect square of the integer sum as before. And this is the typical series that we learned in high school, okay? But here's the thing. As I mentioned, the second problem here is a very popular induction problem because it uses a series identity to work with the induction hypothesis. But here's the thing, instead of working with the induction, what if I was just given the left-hand side, you see? What if I didn't know anything of that? How can I derive algorithmically on the right-hand side is the problem. That has been the paper 3 problem, especially in 2022. That was a spirit. This right now what I'm talking about is something to do with the Fallhaber's formula. But for the sake of this problem, maybe I can show you how to derive the sum of the integer square, and then show you how the algorithm can be applied to derive the other sums as well. Okay, so let me quickly show you. So I want you to start with the I want you to start with the k minus 1 cubic, the binomial expansion. But for this one, I want you to do the rearrangement, right? So let me say that I want to rearrange that to the left hand side and rearrange this to the right hand. Okay. So if you see the difference of cube of the following, and then one way that I can simplify is using the binomial expansion, which I did. So it's 3k squared minus 3k plus 1. Okay, that's great. And I'm going to find the series expression of this from 1 to n. That's what I want to do on the left-hand side and the right-hand side. Okay. And if you look at the left-hand side, I'm going to start plugging the 1 and going all the way up to n. So if you put 1, for example, I get the 1 cubic minus 0 cubic. And if you put 2, I got the 2 cubic minus 1 cubic. And if you put 3, I got the 3 cubic minus 2 cubic. And it goes on and on and on, all the way up to n cubic minus n minus 1 cubic. Right? So that's great. And when you see this, I want you to realize there are some common terms that I can actually cancel symmetrically. Right? So if you see, I got the 1 cubic, I got the 2 cubic, I'm sure I will be able to find the 3 cubic in the same manner. But unfortunately, I cannot get rid of the second term, so that's going to be left over. So now it's going to be in a systematic way, and in a symmetric way, that the second last term wouldn't be able to cancel it out. So this term will be cancelled out with the previous terms here, but then n cubed will be left alone. So that's why we said the sum from 1 to n of this difference of the k cubic and the k minus 1 cubic will result in the n cubic. This is called a telescopic cancellation. So that's great. And that is what I'm going to use on the left-hand side of the sum. Right? So that's what we have. And now remember what I just did is to rearrange that to the other side. So it became positive 3 minus 3k plus 1 before, and I took the sigma on it, right? So, but the sigma has a linearity property. That means you can take the sigma on each side, but I don't know anything about the first term because that's in fact something that I'm trying to derive. And the second and last term, I can use the property of sigma, that's a sum of integer, using the arithmetic series, that will be simply n times n plus 1 over 2. And then the sum of the 1, I'm adding 1 n many times, 1 plus 1 plus 1, all the way up to the nth one, that will give you 1 times n. So I got the n here. I'm very happy with it. And now I'm going to isolate the sum of k squared as a subject, so I shift that to the left-hand side, divide by 3 will give you the identity that you want, which becomes the n times n plus 1 times 2n plus 1 over 6, right? So this is how we derive it using the binomial expansion as well as the telescope cancellation. This is a very typical way to derive. There are many, many different ways, okay? Popular for the exam. But if you will develop this idea into further, right? What about the sum of cubes? What about the sum of quartic? Well, I can give you surely one way to do it, of algorithmic way, as we have seen before. If I define this power series as the SRn, but I want you to realize now I'm going all the way up to, what is it, the n minus 1, okay? I don't go up to n terms, so that's the definition of SR at the moment. And what you can do is that you're gonna, as we saw before, if I want to derive the sum of integers square, what we do is to work with the k cubed minus k minus 1 cubic, and then see the difference, because it's gonna cancel out the leading terms such as k cubed. Right, so then if you take sigma on it, then you would just deal with the sigma k square. For example, if you want to deal with the, let's say that I want to do sigma, for example, k to the power of 3, right? So then the first way I'm going to do is I'm going to work with the k to the power of 4, you see, minus k minus 1, 4. So as you can see, this is going to, get rid of the k to the power of 4 term, so it's going to be some term with the k cubic on and on and on. And if you take the sigma on it, on the left hand side, I'm going to perform the telescopic cancellation. On the right hand side, you just take the linearity of a sigma, isolate the k cubic, and then simplify accordingly, right? So that's what it means by this difference equation. So as you can see, if you go for the n term and then subtract by the n, you can come out with the last term and then derive algorithmically using the previous terms, such as the sum of integer and sum of integer square, right? That's how we can do it. But let me try to do that and then give you like a list of it, right? So for example, however, I want you to realize I'm now going from 0 term to the n minus 1 term. So if I do the same thing, for example, sigma from 1 to n over k was defined as n times n plus 1 over 2. However, in this case, if it had been s1 over n, that would have been, sigma k is equal to 1 to n minus 1 over k. So this time I go 1 less. So this would have resulted in, n times n minus 1 over 2. And then vice versa for the, square, cubic, on and on and on. And if I give you the list of it, it looks like this. This is the sum of squares going from the first term to the, 0th term to the nth terms. That's why we see the difference, because this is going to be sigma k is equal to 1 to n minus 1 k squared. That's n minus 1 and 2n minus 1 over 6. And if you expand, you will, that's not that. This is the one we have. So this is going to be, n minus 1, 2n minus 1 over 6. And this is the n and n minus 1 over 2. Right? So I just expand it out for you. Okay, no problem. And you can do this on and on and on. This is a sum of cubes, but from the 0th term to the n minus 1. This is a sum of quartic, etc., etc. Right? So if you look at the listing of this, you don't really find any pattern other than those coefficients, right? So I see those coefficients as 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, and 1 over 7, things like that. And you got all half here, and then now it changes, right? So I don't know how to make good use of it, right? But here, if I quickly show you how you can actually see the pattern, is to derive by the common factor. For the first one, I want you to factorize by 1, the second one by half, third one by 1/3, and then fourth one by quarter, etc., etc. And then if you look at the coefficient, you find the pattern of it, because those numbers appear repeatedly, right? So what I mean by that is, if I factorize by half and somehow I multiply these binomial coefficient, for which you can sort of see why, because it was deriving something from the binomial expansion from the telescopic cancellation, wasn't it? But then now I see those leftover numbers. I'm not looking at the binomial coefficient, all right? I'm looking at the leftover after working with the binomial coefficient. I have 1 here, and I have a negative half, okay? I got 1 negative half and 1/6. 1 negative half, 1/6. 1 negative half, 1/6. And 1 over 30, negative 1 over 30. 1 negative half, it's supposed to be 1 over 6, sorry, it's a typo. It's supposed to be 1 over 6, don't get me wrong. Negative 1 over 30.
1, negative half, 1 over 6, negative 1 over 30, positive 1 over 42. All right, so those numbers appear repeatedly if I factorize by those things as a 1 over n, right? When the n was given to be 1 over r, when the r was given to be 1, 2, 3, 4, 5, 6, and then match with the binomial coefficient, the leftover coefficient of those series tends to be in a sequence, right? Those numbers appear repeatedly, and that numbers we call it Bernoulli number, all right, from the power series, which we could have seen from the November and May 2022 paper 3 problems working with the power sum, right? So yes, those are the numbers that we have seen repeatedly. 1, negative 1 over 6, as you can see, 1 over 6, so 5 over 6 in the previous question was a mistake. 0, 1 over 30, 0, 1 over 42. Right? That's brilliant, right? That's brilliant. And if I give you further list, it goes on and on and on like that, from which you can see the odd terms tends to be 0, okay, other than 1, right? Other than 1, all the other terms only have contained the even numbers, okay? So that's great. So using the sigma definition of the power sum, I can define now as the following. You know, with the r, I did the 1 over r plus 1, and then this, if I factorize by the binomial coefficient, then voila, you're gonna always end up with the Bernoulli number as the coefficient of the sequence, right? But of course, I cannot just claim it. I just witnessed, I observed it. You should be able to prove it. Right? That would be a very good IA topic. But I'm not gonna do that right now because I just want to use this observation to derive the Maclaurin series of a tangent, right? This is the second part that I need from the exam question that's going to somehow develop into the Maclaurin series of a tangent. But this is marvelous, isn't it? So we don't learn these numbers. However, we could see it coming from our exam. I didn't quote any of the textbook from college. This is just a straight up question from the paper 3 in 2022. All right, but what's the meaning of this number is I'm going to now go back to the function that we were dealing with, the hyperbolic cotangent in the previous slide. In fact, I multiply by the x over 2 to induce only the even term, didn't I? And as I mentioned right now, I got the Bernoulli number. Other than the B1, everything is even term, right? So I'm going to then associate that hyperbolic cotangent with this series and then see what I can derive for the Maclaurin series of tangents. So let's have a look at the third part of this video again, but this time inspired by textbook problem, okay? So generating function for the Bernoulli number. Let's have a look at what I mean by the generating function. This is another Hayes differentiation problem. I believe it's chapter 16, 17, something like that. And in the question number 8, you were to differentiate this function here to find the maximum minimum, all right? And this is actually one step close to a marvelous function the Euler used to derive the Maclaurin series. And let me give you by the graph, okay? So the question gave you e to the power of x over x minus 1, which obviously has a vertical asymptote of x equal to 1, and horizontal asymptote is probably x goes to 0 as horizontal asymptote would be y equal to 0 as x goes to negative infinity, right? All right, so when we see that, it's one step close. It's one step less of the function that Euler used. In fact, if you interchange this e to the power of x and x, if you transform that, if you replace them, so instead of e to the power of x on the top, I'm going to put x on the top, but denominator making e to the power of x minus 1 makes this function, okay? And this function, my friend, somehow is relevant to the Bernoulli number that we were talking about, so, right? So what I'm saying here is this is a very closely related function that you have seen from the from the textbook, right? So you can gain those insights. Let me show you what's so marvelous about this function, okay? So I got the x over e to the power of x minus 1, and let me give you the Maclaurin series of this. I just done the computation for you. In fact, if you try to find the Maclaurin series of this, right, you differentiate once, and if you try to put x equal to 0, you see it's indeterminate. So you actually have to use L'Hopital or limit law to derive the coefficient. In fact, it's not that complicated. It's quite trivial. Okay, so I've done it for you, right? You will have an indeterminate case. Not a problem. You can easily use the Maclaurin series and you can derive the coefficient, no problem. So as you can see, I got this form. But in fact, you know what? If I then make association with the Bernoulli number, in fact, it is made out of the Bernoulli number by over n factorial, right? So number that we saw, I remember it was like 1 and negative half. Remember, like 1 over 6. Exactly. Those are the Bernoulli number, wasn't it? And in fact, if you do that, it's the same thing, but divide by the k factorial, you get the following exact same coefficient. In fact, This is called the generating function for the Maclaurin series because it generates the Maclaurin series for you. So it generates the Bernoulli number using the Maclaurin series, right? So where the B0, B1, B2 are given as such, and if you actually divide those things by 2 factorial and 4 factorial, you end up having the same coefficient as you can see from here. This is great. Okay, so from the second part of the video, we were using what is it? The power series and divided by the 1 over n plus 1, and then also factorized by the n plus 1 choose our coefficient, binomial coefficient. We saw the Bernoulli number. And now using the Maclaurin series of this generating function, I see the Maclaurin series also. Let's make a comparison, right? Let's try to make a comparison, right? This is a great function. But I have a problem with this function. The problem I have here is, who is my enemy with the Bernoulli number? Right, there's a special odd number. In fact, the odd term that I can only have is B1. The other terms are always given by the even, isn't it? The 0, 4th, 6th. Of course, you have to prove it that all the even number, all the odd number other than the B1 will be 0. You didn't prove it. I'm just stating the fact, but it would be a very good IA topic. But if you can see, maybe I don't want to deal with the, I don't want to deal with the odd number. Right, so this odd number was multiplied precisely to the linear term because it was a b1, right, multiplied by the x. So if you add by x over 2, I will only associate with the even terms. Okay, I only deal with the even terms of the Bernoulli number over the n factorial. So let me try to do that. Why not? Okay, so if I add by the x over 2, but on this side, I'm going to simplify the right-hand side further. Okay, let's put them in the common denominator. Well, sorry, I got the Maclaurin series first, didn't I? And I add by x over 2, and you realize I get rid of all the odd terms, which is just even terms in here. And in fact, you have seen this Maclaurin series in the first half. You actually have seen this in the first half of the video. The first part of the video where it was something to do with the cotangent. Hyperbolic cotangent x over 2 times x over 2 was giving you this series, okay? But let me try to simplify, in fact, this gx first. Well, when we add by the x over 2, making the common denominator. So let's try to make into the common denominator 2 times e to the power of x minus 1. Why not? And then let me try to simplify the numerator. If I simplify the numerator for you, it looks like this. Hold on a sec. I got the e to the power of x plus 1, e to the power of x minus 1 here, okay? And then we've seen this identity while working with the complex number that if you multiply by its conjugate, which is, well, not the conjugate, but, e to the power of negative x, but half it. So I got the e to the power of negative x over 2, and I'm going to do the same thing, and I'm going to multiply, I'm going to distribute it like that. If you do that, I get this, I've just done that. So I get this sum of the growth and decay as the following, for which it induces, what is it? The hyperbolic. Very good. On the numerator, that's a sum, that's a hyperbolic cosine. On the denominator, that's a difference, that's a hyperbolic sine. Okay? So that's great. So I can use the, what is it? The hyperbolic cosine of hyperbolic sine is hyperbolic cotangent, wasn't it? So that was the definition that we learned anew. So that's marvelous. I just divide by 2 arbitrarily just to, show you more directly. That's hyperbolic cotangent. Oh my God, that's brilliant. So the gx of x plus 2 was x over 2 times that, but now this will be the x over 2 times the cotangent, hyperbolic cotangent x over 2, which we have seen in the first part of the video, didn't we? Right, so we started with the exam question of 2021 paper 3, which we used the complex number to interchange between the trig ratio and the hyperbolic trig. And then somehow we managed to come up with that identity, and the x over 2 for the x over 2 times hyperbolic cotangent. We even saw the Maclaurin series of it, didn't we? Which was purely made out of the even term. And I'm going to use that right analogy to combine together, all right, for the next final stage of the video. So the first part of the video was to use the complex numbering trick to associate with the hyperbolic trig. The second part was the power sum, right? We talked about how to derive the sum of integer square, and how can we put it into the cube, quartic, 5, and 6. And then we saw the pattern of those coefficients using the Bernoulli number. And then third was to use a generating function, which was very similarly given in the textbook of Hayes on the chapter differentiation. And then so his Maclaurin series actually becoming the same thing of the function that we saw in the first video. So for the final stage of the video, I'm going to combine all these three together to derive the general term of the Maclaurin series of a tangent. Oh my God, let's see how we can do that. Okay, so now I'm going to have a look at the general term for the Maclaurin series of a tangent. So now we saw this is the first part of the video, right? This was the first part of the video. We already found the Maclaurin series of the, what is it? The x over 2 times cotangent x over 2. But then we also, so then, you know, we realized this is something to do with the Bernoulli number. As if you actually try yourself with the 1/2 and 1/6, things like that, you see this, right? And now I'm very happy that I don't have to deal with the odd term. Everything is made out of the even term. And in fact, this was also the same as what? It was the special g function, the generating function, which was x over e to the power x minus 1, but I had by the x over 2. Didn't I? Okay, that's great. And then, so now I can associate this series with the Bernoulli number. So that's the relation I'm going to associate with thanks to my first, second, and third part of the exploration. Okay, that's great. So let's make analogy, right? So now I got the x over 2. Cotangent is same as the, you know, the even term of the Bernoulli number. So that's brilliant, right? So, but I don't like working with the x over 2. Maybe I multiply by the reciprocal, top and bottom, the 2 over x. Right, let's do that. So I got the hyperbolic cotangent Maclaurin series expressed as the Bernoulli number like that. Okay, but maybe I'm not so keen with the hyperbolic trick, right? Maybe I don't like it too much, right? So for example, if I have a hyperbolic, for example, cosine, you know, remember what we did? If you don't like it so much, what have you done? You know, I could maybe put the I theta there, which would have given you to be the e to the power of I theta plus e to the power of negative I theta over 2, which is the cosine theta, isn't it? So if you put the complex identity onto those hyperbolic trig functions, such as sine, cosine, but in this case, cotangent, it can convert into the trig ratio. Okay, let's see what we can do using the hyperbolic sine and hyperbolic cosine. So this is the simplified form after multiplying by the 2 over x, no problem. The power reduced by 1, so now it became an odd term, right? So that's great. And now if I let x to be ix, why are we doing it? Because I want to now make from the hyperbolic to the right angle triangle, right? So that will then convert, you know, so this is the hyperbolic cosine of a hyperbolic sine. But if you put the ix, as you can see, this is going to be simply just a, what is it? Cosine theta. This is a negative sine x, wasn't it? You know, we saw that before. Right, so this, if you rationalize, I got the negative I cotangent x. So that's brilliant. That's what I did on the left-hand side. Well, of course, on my series, I'm going to replace the x with the ix as well. And then it simply becomes as the following. But of course, I can simplify this even further by using maybe the expansion, right? So I got the, what is it? 2ix to the power of 2n minus 1, right? So maybe, you know, I take the power respectively, so it's going to be 2 to the power of 2n minus 1, I to the power of 2n minus 1, x to the power of 2n minus 1, right? Is what I see. But on that one, you know, I can decode even further because it's got the I to the power of 2n times 1 over I, doesn't it? And then the I to the power of 2n is negative 1 to the power of n, right? It's an alternating term. So I can now get rid of the I term like that. Right, so I'm going to do some bit of more of modification with the algebra, as you can see, to simplify even more. Right, so that's great. So yes, that's what we just talked about, right? But you know, I got the negative 1 as well, so it's over 1. But if you rationalize, I got this, so negative 1 can be put back into the negative 1 to the power of n, so it would be just given as such. So that's great. Okay, that is great. However, you know, I think I already had the negative I on the left-hand side, so if you divide, you know, this will have something like the negative I also, but it cancels out. So thanks to the algebra, so now I have been left with just the Maclaurin series of the cotangent like this. This is a one step away of deriving the Maclaurin series of a tangent. So that's great. But from here now, I'm going to use a trig identity to convert from the cotangent. But check this out. You know, this is why they don't ask you to derive the general formula of the Maclaurin series of tangent, in this case cotangent, because those coefficients is not in the syllabus. But it's very closely related to those problems already asked in the exam, especially with the paper 3. So what my point here is, it's very, very very good topic for the IA or extended essay. Okay. So the another trig identity that I'm going to associate with the tangent and cotangent is the following. If you actually, you know, use this identity, you can convert back and forth, right? For example, you know, this is equivalence. Let me try to derive it. Cotangent is a 1 over tangent, and minus 2 times, I'm going to use double angle of tangent, but reciprocate. So it's going to be 2 tangent x. And then on the numerator, that's going to be 1 minus tangent squared, thanks to the double angle of tangent, but reciprocate because this is a 1 over tangent to x. So that's what I'm doing, right? And then it cancels out. So if you then put it into the common denominator, what happens? It's going to be tangent x. If you put it into the common denominator, that's going to be 1 minus 1 plus tangent squared. So it cancels out. So it cancels out, then voila, you got the tangent x I'm very happy with. Okay? So that's great. So tangent x is equal to that. So why I'm doing that is I already have the Maclaurin series of a cotangent, don't I? So then if you use the Maclaurin series of cotangent, but also cotangent 2x, because you just have to substitute with the x with the 2x, you can derive the Maclaurin series of a tangent. Let's see how we can do that. I already have the Maclaurin series of a cotangent. I just use the 2 cotangen's, and then I factorize with the common factor. Okay? And then if you then try to simplify further, that will give you the Maclaurin series of a tangent. Right? So this finalize the Maclaurin series of a tangent. See, derived from the Maclaurin series of a cotangent using the trig identity. Let me quickly show you more detail with the algebra. Maybe I can do that, right? So cotangent minus 2 cotangent 2x. So this was the Maclaurin series of a cotangent, wasn't it? Okay, so we saw that tangent x is cotangent x minus 2 cotangent 2x. We saw that, right? So what I just did on my template here is to use the formula right away. You know, you already got the cotangent, so I'm going to use it. So it's going to be sigma minus 1 to the power of n, b over 2n, Bernoulli number, 2 to the power of 2n times x to the power of 2n minus 1 over 2n factorial. So that's great. And I'm going to do the same thing for my second term. So it's going to be minus 2 times sigma. Now I have a cotangent 2x. So it's going to be exactly the same, right? It's going to be exactly the same. But I'm just replacing the x to be what? 2x is what I'm going to do, okay? So this x, I'm going to change into 2x. That's it. And then you combine them together. So this is going to be sigma. And then what happens with the first term is what I have here. And then the second term is going to be that. But don't forget to multiply by 2, okay? So I just group them together like that. But multiply by negative 2 just to put it into the same sigma and then combine them together. But it's not that bad, right? Because you will have already the common factor of, what is it? Negative 1 to the power of n over 2n factorial. You already have that, I believe. There are quite a few terms already being simply can be seen. So I got the negative 1 to the power of n as a common factor, 2n factorial as a common factor, b2n common factor, 2 to the power of 2n common factor, x to the power of 2n minus 1. Actually, all the term there, isn't it? So I have a b2n, 2 to the power of 2n, x to the power of 2n minus 1 is what I've got. So then the leftover will be 1, right? Minus 2 times 2 to the power of 2n minus 1 is the leftover part, which I have already put nicely on the slide. So if you simplify that, by this trig identity, you get this tangent form, right? So this is which we saw. So this is the formula of the Maclaurin series of a tangent. As you can see, there's a reason why it's not really discussed in the paper 1, 2, or even 3, because in order to put this in the 3, they have to polish this up very well. In fact, I think if they combine paper question 1, 2 together to give you this problem, it's examinable for the paper 3, but not just one question alone, because it will be too lengthy, as you can see. But a very good IA topic, because I want you to realize all this intuition, all this inspiration came down from all the exam questions and then the textbook. I didn't do anything else further, right? I got the generating function from the textbook. I got the the Bernoulli number from the analyzing the power series from the 2022 exam problem, and all this hyperbolic function and trig and the complex identity were paper 3 on the 2021. You see, we're not doing anything fancy. Okay, but if you combine them together, they can be elaborated more, and it can give you even more exciting mathematical aspect of the trigonometry complex number and infinite series. Okay, so that's great. So that's pretty much it for me today, right? So I just want to show you the general term of the tangent. The reason we are not learning that, but only asking you are only asked to find the first 3 terms, right? So that's a typical example. But to find the pattern, we got to know more. But of course, the way I talked about today is a very concise version. You're not going to write your IA paper your IA or extended essay like the rhetoric I gave today, because I omitted a lot of proofs, right? A lot of justification how I can come up with the generating function. I cannot just say I've seen it from the textbook, right? But of course, those things has to be elaborated a bit more, especially with your own tone, right? So your own character of explaining things is the way that you're assessed for the IA, okay? But the general structure you can write. But yeah, I want to show you, therefore, it's important for you to read books. Attempt with the textbook, it's very important. They spend tremendous amount of time to create those marvelous textbook, and you really want to benefit from it. And I cannot say only one textbook is the good, right? Good is the good one. There are many different characters depending on the country, for example, right? For example, Hayes would probably have a background of a high school certificate from Australia. On the other hand, the Oxford or Cambridge will have some characteristics from the A level, right? It really depends. On the other hand, IBID, which is a good old but gold, would have a very challenging aspect because the instructor was a very, very encouraging student, right, students to work more. So those different characters can be seen differently on the textbook. So I really want you to enjoy them. Do not rely too much on the online resource. Do not rely too much on the question bank or the revision websites. They're equally great, but only to my knowledge, maybe for the unit test, maybe not upcoming exam or paper 3 or IA or EE. The books are as good as it gets. Okay, that's the lesson of the day, and I'll see you next time. Thank you.